In progress.
Welcome to a lecture. Today's topic is a controllable series compensation. This is our topic. But before proceeding to the topic, first we will see the basic of series compensation. So this is the line, and series compensator or series controller is inserted in series with the transmission line. And what is the series controller or series compensator? A series controller could be a variable impedance. This is important. Either it is a variable impedance or such as capacitor or inductor, which may be connected in series with the transmission line, or power converter base variable voltage source. So it may be a voltage source, it may be a variable impedance. That is, impedance multiplied by current is nothing but the voltage. So here it may be a variable impedance or variable voltage source of the main frequency, or it is a synchronized. In principle, all series controller inject the voltage in series with the line. So all type of, either it may be a variable impedance type or it may be a variable voltage source converters may inject a voltage in series with the transmission line. Now, as long as the voltage in phase quadrature with the line current, the series controller only supplies or consume variable reactive power. So whatever the voltage which we are injecting either by the variable impedance or it may be by the converter base voltage source is there, that voltage should be in phase quadrature with the line current. Under such condition, the controller or the series compensator is going to consume or supplies the reactive power. So this is the things which we have already learned. In the series compensation, we have seen the advantage of series compensator in the power handling capacity, that is increase in the power handling capacity with increase in the factor K, which is called as a compensation factor, that is XC upon X. Second, we have seen the advantage of series compensation, improvement in the transient stability. Then it also mitigates the unwanted oscillation in the power system. Now, today's topic is a controllable series compensation. The controllable series compensation is divided into two major parts. One is the switching converter type series compensator. It is called as a static synchronous series compensator, SSC. So this is some basic diagram. This is the sending end voltage. This is receiving end voltage. It is a two machine system. This is transmission line reactance XL. And here it is a static synchronous compensator, SSC, is inserted in series with the transmission line, which is going to inject the voltage in phase quadrature with the line current. So this is one type of the controllable series compensation. Second is the thyristor base. So in the thyristor base, which is called as a variable impedance type. This is called as a variable impedance type series compensation. So this is switching converter type series compensation. It is variable impedance type series compensation. In variable impedance type series compensation, there are again three parts. One is the GTO, that is a gate turn off thyristor control series capacitor, which is called as a GCSC, whose basic diagram is, this is the basic diagram. This is the capacitor which is inserted in series with the transmission line. And our objective is to control the voltage across capacitor VC. This is the line current. GTO is connected in anti-parallel. So it acts as a switch. By controlling this switch, it is possible to control the voltage across capacitor, and hence we obtain the voltage E, which is inserted in series with the transmission line for the compensation purpose. That is the series compensation. Second type of the variable impedance type series compensation is the thyristor switch series capacitor, TCSC. So there are number of capacitors are connected. say there are n number of capacitors are connected in series with the transmission line, and it is shunted by the pair of SCRs, which is connected. Those are connected in anti-parallel. So when these two SCRs under the off condition, definitely the voltage across capacitor VC1 is going to appear in series with the transmission line, and so on. So this is the step-like variation in the series with the transmission line. So it is, therefore it is called as a switched converter, a switched capacitor. It is not a smooth control, it is a switching mode is over this one. And third one is the thyristor controlled series capacitor. In thyristor controlled series capacitor, a capacitor is connected in series with the transmission line. This is the transmission line current. So this is the transmission conductor, transmission line is there, where the capacitor C is connected, whose voltage across capacitor is going to change by inserting a shunt inductor. So this much part is just like a TCR, thyristor control reactor. So by controlling the thyristor, the effective value of capacitance or effective value of voltage is going to control by this way. So this is the three methods are there in the variable impedance type series compensation, and in switching converter type series compensation is the static synchronous compensator, which we will see one by one in detail. Now, our topic, first one is the we consider GTO, gate turn-off thyristor controlled series compensation. So under such condition, what is the basic diagram? The basic diagram is already we have seen, but we will redraw it. So this is the capacitor. This capacitor is shunted by a pair of anti-parallel connected GTOs across the capacitor. So this is the capacitor, and voltage across capacitor is VC, where our objective is to control the voltage across capacitor. Why we want to control the voltage across capacitor? See here, in our basic diagram, this is the line current, and we want to inject the voltage in phase quadrature with the transmission line current. So therefore, we want the voltage across the capacitor. Here we want the voltage across capacitor over this one. So first, to understand what is the analogy of this circuit, this is the switch. We are acting as a switch where it is a GT1 and say it is a GT2. Two gate turn-off thyristors are connected in anti-parallel, and this is the capacitor, and voltage across capacitor we want to control it. Say for example, it is analogous to the simple switch. Say this is the switch is there. I'm just replacing it by a simple switch for understanding voltage across capacitor. This is VC, voltage across capacitor. This is capacitor, and this is the line current. Okay. When the switch is closed, what will happen? The current is going to flow from the switch, short circuited switch, and it is bypass the capacitor. And when the current is not flowing through the capacitor, voltage across capacitor VC is equal to 0. Whereas when switch is when switch is open, what happened? The current is going to flow from the capacitor and voltage across capacitor is going to appear. So here the voltage across capacitor, it may be written as it is a VC normal, is a normal voltage as per the rating of the capacitor, or it may be say it is a VC maximum voltage that can be appear across the capacitor. So it means that if you want to say voltage across capacitor, the switch should be open, and when the voltage across capacitor should zero, so we make it voltage across capacitor is equal to zero by closing the switch over this one. So now this switch is now replaced by the GTOs, two GTOs in the anti-parallel connected this one. Now, as this is the capacitor, say this is the line current of the transmission line. This is the line current of the transmission line I. Okay, this is the I was this one, and this is omega t. Okay. Now at the maximum value of current, or this is the crest value or peak value of current, the gate GTO, this GTO is turned off. Earlier it is a turn on over this time. So current is going to flow across through the GTO, and under such condition the voltage across capacitor is zero. But as soon as the GTO is say remain close, now here the GT1 is on, so voltage across capacitor VC is equal to 0. Now at this point the total switch, this switch is closed, sorry, this switch is open, means GTO is not going to conduct over this one. So under such condition the voltage across capacitor will be here, and it is represented by, this is the voltage across capacitor in the positive direction. In the negative direction again the voltage is 0. So this is voltage is 0. Sorry, the switch is open, and under such condition it will give the voltage across capacitor VC, isn't it? Now the controlling of GTO is done by turn off delay circuit. Turn off delay angle, this one, isn't it? As compared to the TCR which we have used as a turn on delay circuit, instead of this one we are using the turn off delay circuit, isn't it? Now again we will draw with the change in the system. So change in the turn off this one. Now let turn off delay angle gamma is equal to gamma 1. Let we have turn off delay angle, instead of turning off over here, we will delay it by some angle. So what will happen? The voltage across capacitor up to this one, the voltage across capacitor is 0, whereas the voltage across capacitor is going to increase because there is a turn off delay angle is there, and here we will get the voltage across capacitor VC, where the gamma is equal to gamma 1. So this much is the turn off delay angle. So this is the gamma 1 is the turn off delay angle. Similarly here, this is also the gamma 1. Okay. So this is also the gamma 1 is the turn off delay angle. So it means that if you increase the turn off delay angle, the voltage across capacitor may change, that is decreasing. Again, we will draw this same figure for better understanding. Say this is the current in the transmission line. And so on. So this is the current. Now the capacitor here again, the turn off delay angle is delayed at some different values, so as to obtain the voltage across capacitor will be a variable one. So at this point, your GT1 is on. Let this is on. So the voltage across capacitor is 0, because when this GTO is on in the positive half cycle, the current is going diverted through the GTOs, and the voltage across capacitor will be 0. But the delayed angle will be there. Some delay angle we have used, turn off delay angle. No doubt it is a turn off delay angle. So the voltage across capacitor will be this much. So this is the voltage across capacitor is VC at gamma 1 is there, isn't it? Now in the negative half cycle, this is going to turn off, and when it is turned off, the voltage is 0, whereas in negative half cycle, G2 will be turned on. So here it is turned off, and the voltage across, again there is a more delay angle, so the voltage across capacitor is decreases over this one till it will be a off condition. It is a on condition. So under such condition, GT1 is on, and whereas GT2 will be off. Okay, so here this is the voltage VC at gamma is equal to 2. So we will get how it will be. So this much is the delay angle. Turn off delay angle is gamma 1. Here it is turn off delay angle, which is measured with respect to the crest of the current or maximum value of the current, gamma 2. If again the voltage across capacitor is delayed in the positive half cycle, so we will get again a smaller voltage over this one. So this is the gamma 3, and so on. So finally, our conclusion is that by controlling the turn off delay angle gamma, it is possible to get the voltage across capacitor is variable. So simply by delaying the turn off angle gamma, it is possible to get the voltage across capacitor will be a variable. This is our objective, to get the variable voltage. Now here, this is called as a blocking angle. This much part is called as a blocking angle. Blocking angle zeta, and where zeta is equal to total angle is pi, and it is pi minus twice gamma. Is it twice gamma? So this is the blocking angle, and whereas this is the area, it is turn off delay angle. So when the turn off, during this time, your GTO is going to conduct over this one. So in this way, it is possible to get the voltage across capacitor, variable voltage across capacitor. Under such condition, the gamma range is, what is the range? It is from this angle is, say, a total angle is 90. Here it is a pi, okay, and it is pi by 2. So it is from pi by 2 to pi. This is the range. But in general, it is written as the range of angle, delay angle, turn of delay angle is equal to 0 to 90 degree. Isn't it? It is considered as 0 and it is a 90 degree. So if the turn of delay angle is equal to 90, now we will reach to some when turn of delay angle gamma is equal to 0. What it means? It means that the voltage across capacitor VC is equal to VC maximum, isn't it? When the turn of delay angle gamma is equal to 0. So at this point, the gamma is equal to 0 and voltage across capacitor will be maximum. And when the turn of delay angle gamma is equal to 90 degree, isn't it? 90 degree means over here, it means that it is conducting. And as it is conducting, the current is going to flow from the, say, GTOs, and the current in the capacitor will be 0. And when the current capacitor will be 0, the voltage should be a 0, 1. So the voltage across capacitor VC is equal to 0. So in between 0 to 90 degree, it is possible to change the voltage across capacitor, and hence it is possible to get variable voltage injection in series with the transmission line, isn't it? Now we consider some equation to come out with some equations. This is the current in the transmission line. This is omega t. Current is there. Now at the peak, that is pi by 2. This is the value of maximum current. And here it is the voltage across capacitor when the turn off delay angle is equal to 0. So this is the voltage VC. Okay. Now the voltage across capacitor across capacitor VC is equal to, what is that? 1 upon C integration gamma to omega t into I t dt. Okay. So now see here, at this point, no doubt the voltage is 0, but the current is a maximum. So we will write the equation, instead of I sin theta, we write I 1 upon C integration I cos theta or I cos omega t into dt. So we get I upon omega c into bracket sin omega t and limit gamma into omega t. So we get voltage across capacitor is equal to I omega c into bracket sin omega t minus sin gamma. This is the voltage across capacitor. and we can say that this is for the GCSC, which we have discussing. Whereas if you remember the formula of current in the TCR, which is the function of turn on delay angle. So just I will write by a different color. So I alpha IL, that is current into the inductor, with the function of turn on delay angle, which is equal to V upon omega C into bracket sine omega t minus sine alpha. This equation is for TCR. TCR. What is that TCR? Say in this TCR, we have used in the shunt compensation. This is the inductor, and we want the current to flow, current to control into the inductor with the function of alpha. And there is a SCRs or thyristors, which is connected in anti-parallel. This one. So here, this is the voltage V of the transmission line. It is a shunt compensation. It is a shunt compensation. Okay. So if just look at these two equation, VC is equal to 1 upon omega C sine omega t minus sine gamma. This is for the GCSC, and for the TCR, I alpha, I current in the inductor IL with the function of turn on delay angle, where alpha is the turn on delay angle sine omega t minus sine alpha. So this is some analogous to the TCR, isn't it? So under such condition, there are some analogy between the GCSC and TCR is that TCR is supplied by the transmission line voltage as it is connected into the parallel. So the TCR is supplied by the transmission line bus voltage, whereas the GCSC is supplied by the transmission line current, isn't it? This is first analogy. Second analogy is that the TCR wall is open at current 0. It is going to open at current 0, whereas GCSC wall is going to close at voltage 0. This is the second analogy. And TCR control the reactive current in the inductor supplied with the fixed voltage bus at the controllable admittance, whereas the GCSC control the capacitor voltage. But our objective is to control the voltage VC across the capacitor. So it is controllable. So our objective is to control the voltage across capacitor supplied with the fixed value of current and impedance. This is, isn't it? So under such condition, we can write the similar equation as we know the current IL alpha, which we have derived. It is V upon omega C into bracket 1 minus twice pi 2 upon pi into alpha minus 1 upon pi into sine of twice alpha. This is the equation already we have drawn in the TCR. Now, the similar equation for the GCSC, the voltage across capacitor VC, at the function of turn off delay angle gamma is equal to I upon omega C into bracket, same equation, only the alpha is replaced by gamma, 1 minus 2 upon pi into gamma minus sine twice gamma. So this is the for GCSC, isn't it? Now from this equation, we want to draw the characteristic, or what we want to draw, the relation of gamma and voltage across capacitor. So this is the angle gamma and this is voltage VC. Okay. So this is the 1 pu voltage. This is 0.5. Say this is 0.75 and it is 0.25. Similarly, where gamma, this is start from 0. Say it is 10 degree, 20, 30, 40, and here say it is 45, and here it is 90 degree. Okay, so here gamma is there, and here voltage across capacitor VC is there. Okay, now as gamma increases, this factor 1 minus twice gamma divided by pi is decreases. So under such condition, this is the relation of part of the equation is, so this represent as 1 minus twice gamma divided by pi. As gamma increases, it is decreases, and at 90 degree it becomes 0, isn't it? Whereas the second part, that is 1 minus 1 upon pi into sine twice gamma, isn't it? So here 1 upon pi is remaining. Okay, so 1 upon pi, 1 minus 1 upon pi sine gamma. This is somewhat, first is decrease and then increases. So this is like this. So this is the representation of this part of the equation. Now by adding this to 1, we get the total relation with respect to the gamma. So here it is decreasing and become 0. So this is the voltage VC. This voltage VC with the function of angle gamma. So it is quite clear that at gamma is equal to 0, when gamma is equal to 0, voltage across capacitor is maximum, which we have seen by this diagram. Just again we'll draw because it is somewhat confusing. Turn off delay angle. This is GTO 1, GTO 2. It is connected across the capacitor. And our objective is to control the voltage across capacitor. So this is the current I, this is C, and we want the voltage across capacitor with the function of gamma. So when gamma is equal to 0, it means that these two GTOs or switch is equal to close. It is open, and when it is open, the entire current is going to flow from the capacitor, and the voltage across capacitor is equal to 0. Voltage across capacitor is maximum. So under such condition, at gamma is equal to 0, voltage across capacitor is 0, is maximum. See here in this waveform. So as gamma is equal to 0, here gamma is equal to 0, voltage VC will going to appear in this diagram also, and in this diagram also. See here, at gamma is equal to 0, voltage VC will be its maximum, and as the gamma increases, that is turn off delay angle increases, the voltage across capacitor get decreases. See here, this is voltage across capacitor, it is gamma 1, it is gamma 2, it is gamma 3, and so on. So by increasing the turn off delay angle, the voltage across capacitor decreases. So this is voltage across capacitor decreases. So this is the some operation of GTO Thyristor control series compensation. Now this series compensation is has two modes. One is the first mode is called as a voltage compensation mode. Voltage compensation mode. And second is impedance compensation. This is the second part, is a voltage compensation mode and series compensation mode. Now again, we draw this as already we have drawn this one. So we will use same this diagram. Say this is the current, okay, and we want to control voltage across capacitor. This is our objective. Our objective is to control voltage across capacitor. Now let the current is minimum. Current is minimum. Then we want the voltage should be voltage across capacitor should be maximum, isn't it? Voltage across capacitor should be a maximum. But as soon as the current in the line, transmission line increases, the GTO1 or GTO2 is going to conduct, and part of the current is going to flow from the GTO, and rest of the current, that is the minimum value of current, is going to flow from the capacitor. So we say that the voltage across capacitor will be remain constant, and which is equal to maximum. Again, I'll just explain it. Say VC maximum is equal to I minimum into XC, isn't it? As soon as the current increases, the voltage across capacitor, that is going to increase more than the maximum value. It's a quite obvious. But during that time, what we will do, we will divert the current through the GTOs in such a way that the voltage across capacitor will remain constant, is maximum in the, even though the current is maximum, isn't it? So this is called as the voltage compensation mode, and the diagram, that is VI characteristic under such condition, is like that. So say this is the voltage compensation mode. This is the current I, and here is voltage across capacitor. Say this is the minimum current, I minimum, and this is the, say, I maximum current. Okay. So for the minimum current, the voltage across capacitor should be a maximum one. So it should remain maximum. So it is VC maximum. So this is the case. And even though the current increases beyond the minimum value, the voltage across capacitor should be a 0, isn't it? So this is the working region or working area of TCSC, sorry, GS, gate turn of series compensation under voltage compensation mode. Okay, this is the area. Now, what about the losses under such condition? So we can understand, or we can draw the losses for the voltage compensation mode. Again, this is the current I. This is percentage loss. This is the minimum value of current, minimum value and maximum value. When the current is minimum, so the loss is also smaller. The loss is also smaller. the losses also is smaller. So it represented, this is the losses are smaller. But as soon as the current increases from minimum to maximum value, part of the current is going to flow from the gate wall, isn't it? Part of the current is going to flow from the gate wall. See here, as the current is minimum, voltage is the maximum voltage appear across the capacitor. As current beyond this minimum value, part of the current is going to divert it from the GTOs. Under when the current flow from the GTO, the losses get increases. So losses get increases, isn't it? And whereas when the voltage across capacitor is zero, when the voltage is capacitor is zero, it means that entire current is going to flow from the GTO. So it will represent it as this. So this is the losses, representation of losses under two mode. So upper mode is the when VC at gamma is equal to 0. Means the entire current is going to flow from the GTOs. Isn't it? Very interesting. And whereas under such condition, the current up to this one, the current is going to flow from the capacitor itself. And here voltage across capacitor is gamma will be there. So is the function of gamma, is the function of gamma. Now in impedance compensation mode, in impedance compensation mode, the we can write as the impedance XC is equal to VC upon I, isn't it? Voltage across capacitor divided by current. Now XC is the function of gamma. Why it is function of gamma? Because voltage across capacitor is the function of turn of delay angle, that is a gamma, divided by I. As gamma changes, the voltage across capacitor get changes. When gamma is equal to 0, voltage is maximum. And when gamma is equal to 90 degree, voltage becomes 0. Isn't it? It's opposite to this one. So under such condition, the reactance of the capacitor also get changes. So we can say that the reactance also the function of gamma. So it is the current over this one, and it is represented as a V gamma maximum. Reactance will be there, and this is the maximum voltage across capacitor. So it is VC maximum and current maximum. I maximum. And this is the value is called as a XC gamma maximum, and this is the region. This is the working region under impedance compensation. This is the VI characteristic. It is called as a VI operating region, operating area or region, isn't it? Now what about the losses? The same one. As long as the current flows from the capacitor, the losses will be small. As long as the current flow from the capacitor, the losses will be small. And when the current more than the minimum value, the part of the current is going to divert it from the capacitor, from the capacitor to the GTOs. So this is the representation when voltage across capacitor is maximum, that is VC gamma is equal to 0. Voltage is 0. Maximum current is going to flow from the GTOs. And when the current flow from the capacitor, the losses will be small. So this is VC will be there, isn't it? So this is the losses by impedance compensation. Try to understand one more thing. This is the case when VC is equal to 0, isn't it? It means that current is going to flow from the GTOs. Just try to understand. This is very interesting. Say this is the GTO 1. This is GTO 2. This is capacitor. And VC is equal at function of gamma, isn't it? Now this is the current. Let VC is equal to 0. When VC is equal to 0? When GTO 1 and GTO 2 is in the conduction mode, isn't it? Turn off delay angle is equal to 90 degree. This is the current. Total current is going to flow. This is off condition. So current is going to flow. Voltage is 0. So current is going to flow from here. And under such condition, the losses are going to appear more. And when current going to flow from the capacitor, the losses will be small. So this is VC with the function of gamma is equal to 0. So the losses is more. And when the current flow through the capacitor, the losses will be small. So this is the operation of gate turn of thyristor series compensation. Now it can be explained by some PPTs. We already covered these points, the basic of all these things, transient stability and all these points. Now here, see, this is the controllable series compensation. It has two major category. One is the variable impedance type series compensation and switching converter type series compensation. In switching converter type series compensation, it is a static synchronous series compensation, SSSC, and variable impedance type series compensation has three parts. One is the GTO Thyristor control series compensation, which we have already discussed. This is the thyristor switched capacitor and thyristor control series capacitor. So we have seen in detail the first type. So this is the three types are there, and GTO type thyristor control series capacitor. So this is the basic diagram of GTO GCSC. Under this GCSC, this is the current in the transmission line. This is the voltage. Our objective is to control the voltage across capacitor by proper turn of delay angle. So when the turn of delay angle is equal to 0, turn of delay angle is equal to 0, here voltage across capacitor will be maximum. As the turn of delay angle is gone increasing, the voltage across capacitor will start decreasing. So it can be explained. This is the diagram and the value of current VC voltage across capacitor is equal to I upon omega C sine omega t minus sine gamma, and the working region, region of gamma is equal to omega t pi minus gamma. So this is one which we have already covered, and the blocking angle is equal to pi minus twice gamma. So see, this is the pi minus. So this is from this diagram, it is quite clear. This is the current voltage across capacitor which we want to control. At gamma is equal to 0, voltage is maximum. At gamma is equal to 0, voltage is maximum. Here gamma is increasing, gamma to gamma 1. This much is the conduction part, and this is the blocking region. This much is the blocking, which is zeta. And this blocking is gone increasing, whereas blocking angle also decreasing. Here gamma is decreasing, and turn off delay angle is increasing in such a way that we can obtain the variable voltage across capacitor. This is our objective. Voltage obtained across the capacitor should be a variable one with the help of GTOs, isn't it? Now this is the VI characteristic in the voltage compensation mode. In voltage compensation mode, this is the minimum value of current and this is the maximum value of current. At minimum value of current, VC should be maximum, and as the current increases from minimum toward the maximum value, part of the current is diverted from the GTOs and rest of the current is going to flow from the capacitor in such a way that voltage across capacitor should not increase beyond its maximum value. So hence, this is the working area of GCSC. Whereas the losses under such a voltage control mode, this is the voltage across capacitor is zero. It means that entire current is going to flow from the GTOs and hence the losses are more. Whereas when up to the minimum value of current, the current is going to flow from the capacitor. The current is going from the flow from the capacitor. The losses are small and hence the losses represented. This is losses are very small. But as soon as the current increases from the minimum to the maximum value, part of the current is going to flow from the GTOs and hence the losses start increasing. So this is the working region and representation of the losses under minimum to maximum operation. The second mode of operation is impedance compensation mode. Under impedance compensation mode, we will keep XC is equal to VC maximum divided by the current maximum. As we know that the value of XC, voltage across capacitor is the function of angle gamma divided by I maximum, and therefore the reactance XC also the function of turn of delay angle. So this represent, it is just similar to the TCR. So it is the reactance X or admittance. It can be represented as admittance and reactance is that this is the region, working region. And under such condition, when the voltage across capacitor is zero, entire current is going to flow from the GTOs and large power loss going to appear in this transmission line. And when the current flow through the capacitor, the losses will be smaller. So this is the end of GCSC. Thank you.